Hey folks, today we continue working with integration by parts, and let's start off by reviewing the integration by parts formula. Integration by parts. If u and v are functions of x and have continuous derivatives, then the integral u dv is equal to u times v minus the integral v du. We are expressing, the integration by parts formula allows us to express an original integral in terms of another integral. Often our choices of u and dv in the original integral will make the second integral here easier to evaluate. The choices of u and dv are important. As a result, consider the following guidelines. Some guidelines for integration by parts. We will try letting u be that part of the integrand whose derivative is a simpler function than u. Then dv will be the rest of the integrand. Try letting dv be the most complicated part of the integrand that is easily integrated. Then we will let u be the rest of the integrand. Now please note that dv involves the dx from the original integrand. All right, let's try a quick example here. Here we are going to use integration by parts to integrate natural log 2x over x squared dx. For this first example, let's try letting u equal the natural log of 2x, then dv will be a 1 over x squared dx. Or we could rewrite that as x to the negative second dx. We must compute the derivative, or the differential, du. So the derivative of natural log 2x will be 2 over 2x. Do not forget the chain rule to get the 2 over 2x dx. To determine v, we have a little mini integration problem to do here. We know dv is equal to x to the negative second dx. So using the power rule of integration, we can determine that v is the antiderivative of x to the negative second dx. So we get v is negative 1 x to the negative first, which I will rewrite that as negative 1 over x. Now when I do an integration by parts problem, I always like to write down the original integral. So here it's the integral natural log 2x over x squared, that's a bad x, dx. And then I write down the result of integration by parts. And we know integration by parts is u times v. So I'm going to write that as negative 1 over x, the natural log of 2x, minus the integral of v, which is negative 1 over x, times du. Notice that du would simplify to 1 over x dx. Cleaning this up just a little bit, we have a negative 1 over x, the natural log of 2x, plus the antiderivative of 1 over x squared dx. Our final step, because all we have left to do, is to integrate this 1 over x squared dx. That gives us negative 1 over x, the natural log of 2x, minus 1 over x, and then don't forget your constant of integration. Now let's see if we can come up with another example here. Here we're going to use integration by parts to evaluate the integral e to the 3x cosine 4x dx. Here I'd let u equal cosine 4x, and dv will equal e to the 3x dx. Du, the derivative of cosine 4x, is negative 4 sine 4x. And then v, We just have to integrate e to the 3x dx. So we get v as a 1/3 e to the 3x. Now you may be asking yourself, when we look at this integral, e to the 3x cosine 4x dx, how do you know which one of these pieces of the integrand to let equal u? How do we know to let u equal cosine 4x as opposed to letting u equal e to the 3x? Really no good answer to that, except I look at this integral e to the 3x cosine 4x dx, and I think e to the 3x is the most complicated part of this integrand that it was easy to integrate. Very straightforward. It is easy to integrate cosine 4x if we had opted to let that be dv, but I think e to the 3x is a little bit more complicated than a cosine 4x dx. So continuing, I will write down my original integral, which is e to the 3x cosine 4x dx. And then thanks to integration by parts, we have u times v. And I'll write that as a 1/3 e to the 3x cosine 4x minus the integral of v du. So it's minus the integral of v and then du. Notice du is a negative 4 sine 4x. Then we have a dx. My next step is to clean this up just a little. 1/3 e to the 3x cosine 4x plus 4/3 the integral e to the 3x sine 4x. Notice the integral we are left with now. The integral of e to the 3x sine 4x dx. It looks very similar to what we started off with, which tells me we need to use integration by parts a second time. We need to crank this integral through integration by parts. So on our second application of cranking this integral through integration by parts, you know what, I think I'm going to change colors of my pen. And I'll go to a red pen here. Very similar to how we started the problem originally, I will let u equal sine 4x dv equals e to the 3x dx. Du is going to give us a 4 cosine 4x dx, and v is a 1/3 e to the 3x. All right, I'm going to change back to my blue pen and continue with this problem. Again, I write down the original problem, which is e to the 3x cosine 4x dx, and that is equal to, now our first iteration of integration by parts, it gave us 1/3 e to the 3x cosine 4x plus 4/3. And now I'm going to put a square bracket because I am now cranking this integral through integration by parts. U times v, so that's a 1/3 e to the 3x times 4 sine 4x, u times v. There should be no 4 there. Let me just kind of scratch that out. Sorry about that. Minus the integral v times du. So v times du is a 1/3 e to the 3x times 4 cosine 4x dx. Let me put a square bracket there. Okay, getting kind of a mess here, but look what happens when we clean it up. 1/3 e to the 3x cosine 4x plus, now I'm going to distribute that 4/3, and I get a 4/9 e to the 3x sine 4x minus, 1/3 times 4 is 4/3. So 4/3 become, I could rip it out front of the integral here, distribute that 4/3 here. So this 4/3 get distributed by that 4/3 will give me a 16/9. The integral e to the 3x cosine 4x dx. At this time, it's like, well, wait a minute. We now have an integral that's exactly the same as the integral we started with. This integral is the same as this integral. This is exactly why when I use integration by parts, I tend to always write down my original integral and then cranking it through the integration by parts process. To finish off this problem, rather than take this integral through integration by parts again, we've already done that. We did that up here. That was our first step. I can treat this as an equation. We have integral e to the 3x cosine 4x dx equals, this is an equation. So if I just add 16/9 integral e to the 3x cosine 4x to both sides of the equation, I will get 25/9 integral e to the 3x cosine 4x dx equals 1/3 e to the 3x cosine 4x plus 4/9 e to the 3x sine 4x. Now if I multiply both sides of this equation by 9/25, I get the antiderivative for e to the 3x cosine 4x dx, the problem we originally started with, is equal to 9/25. I have to multiply this side by 9/25. And if I multiply everything over here by 9/25, I will get 3/25 e to the 3x cosine 4x plus 4/25 e to the 3x sine 4x. And then don't forget the constant of integration c. So to recap on this problem here, we look at the original integral we started with. We let u equal cosine 4x, dv equal e to the 3x dx. This is the result. This line right here is the result of our first application of integration by parts. When we simplified the right side, we pulled out a negative 4/3 here and made it plus 4/3. We ended up with an integral that we then cranked it through integration by parts, which is the step I have in red here. And then after we cranked the second integral through integration by parts, our second application of integration by parts, we eventually ended up with an integral that's exactly the same as the integral we started with, which is why writing this down as an equation allows us to finish the problem using basic algebra and solving. Thanks for watching. I hope this has given you 2 more examples in the process of integration by parts.